Here we have two molecules of 2-chlorobutene, but they are different stereoisomers. In this video, I'm going to quickly cover how we decide which stereoisomers we have using both the EZ and cis-trans terminology, settling the confusion for you once and for all. The first thing to consider is that these molecules meet the essential criteria. They have the non-rotational pi bond, and each carbon in the C double bond C is bonded to two different atoms or groups. Let's start by studying how we decide whether it's E or Z then. For this, we're going to use the Cahn-Ingold Prelog rules, which assign priority to the groups surrounding the carbons in the C double bond C using atomic numbers. Now, we only initially look at the immediate carbon atoms connected to the C double bond C for this. For example, in the top left, we've got hydrogen, which is of course 1, and in the bottom left, we've got a 6 on the carbon. We're not looking at the entire CH3 necessarily here. We're just looking initially at that immediate atom. It's a carbon here. It's got a 6 for its atomic number. On the right-hand carbon, top right-hand corner, we've got another 6 for that CH3 carbon. And then in the bottom right, we've got a 17 for that chlorine. Each carbon needs its own high priority group here, which is decided by which of the two has got the higher atomic number from the groups we've allocated here. That means we've got the high priority group of the left-hand carbon as the CH3 group there, or just the carbon we could consider. And for the right-hand carbon in this particular stereoisomer, it's going to be the chlorine, because that's the 17, much greater than the 6 of the carbon that was above it. We then look at their positioning. Top side versus bottom side here, not left and right. Here we can see that the two atoms with the higher atomic numbers from each carbon are on the same side, the bottom side in this case, making this the Z stereoisomer. If we had one above and one below, then as you can see on screen now, this would be the alternative E stereoisomer. What lots of people then struggle with is how we allocate cis-trans, because this doesn't use atomic numbers, and there's some mixed messages out there by different exam boards and different textbooks saying it is only ever hydrogens or it can be things other than hydrogen. So let's clear that up. Instead of the atomic numbers, we're going to be looking at two of the substituent groups, that's one from each carbon in the C double bond C, need to be the same as each other. So this could be two H's, it could be two benzene rings, it could be two bromine atoms, or in fact, just like it is here, it could be two CH3 groups. How these are then positioned decides the stereoisomer notation. Trans if they're across from each other, that's one above and one below, and cis if they're on the same side as each other, so that's both above or both below. Here you can see I've labelled that up with the blue labels on screen. Someone once described to me that the cis here is like their sisters. So from the same family, they're on the same side, and trans is like transatlantic. So we're crossing over from one side of the Atlantic to the other. So do you think you've got it? What about this molecule then? It has a tricky twist to it, which can make it tougher to allocate. Click the link on screen now to go straight to an explanation of this one, or follow the other links to my curly arrow summary work, or perhaps even some unified chemistry exam paper walkthroughs. Either way, as always, happy revising.